Yeah.
If their I is bidding more than their J, then definitely he will get the proper good.
Okay.
And if the bids are equal, then they'll share it equally.
Right.
And if the bid is lesser,
He will
then
not
he
get
will
anything. Right. So if the bid of the ith player is greater than the bid of the jth player, obviously the ith player gets the good and his payoff is what he values it minus how much he bids for it. Right? Assuming that both the players put the same bid, they need to toss a coin. Right? And then depending on the outcome of the coin, the good is allocated. So therefore the probability, this is the expected value of that toss. Vi minus Bi upon 2. 0.5 into Vi minus Bi. And if your bid is less than the bid, the ith player's bid is less than the bid of the jth player, then you don't get anything, right? Okay. Now,
So I don't get what is BI minus BID.
Bi is the bid that you have. The amount of money that you bid.
That's BI.
Yeah, Bi is your valuation.
Yeah.
So your payoff, if you win the good, is Vi minus Bi. Because Bi is what you pay, right? Yeah? Sure?
It's the surplus that we have.
It's the surplus that you have from the transaction.
Yeah.
Correct. P is the price, but we are not looking at BIs, the bids. The actions are the bids now, right? Yeah. So it's ultimately the price P. If you pay the price P, but the price is not the action. The actions are bids. Right? So you're right. So Vi minus Bi upon 2 and 0, Vi is less than Bj. Okay? Alright? Okay. Now, so we have a Nash equilibrium if, okay? So we are trying to maximize over Bi. So we have a Nash equilibrium, okay? If for each Vi, okay, we have a right? We have a Bayesian-Nash equilibrium. What does it mean? See, what are we trying to maximize? We get Vi, Bi. This is the expected value of the payoff. Right? When you get Vi minus Bi, if Bi is greater than Bj, which is a function of Vj, the valuation of the jth player. So what you bid is above what the other person bids, you get the good. Right? If what you bid is the same as what the other person bids, then you get half of Vi minus Bi. And if what you bid is less than what the other person bids, you don't get anything. So the expected value of what you bid is this. This is the expected value of what you bid. Vi minus Bi into the probability that Vi is greater than Bj plus half into the probability, half Vi minus Bi into the probability that Bi is the same as Bj. Right? If we can find a Bi which solves this and also Bj which solves this, right, then we have a Bayesian-Nash equilibrium. That is, each person is maximizing his, the bid that each person is making is maximizing the expected utility of that person given the optimal choices by other players and their beliefs which are encapsulated in this probability structure, right, okay, about the other players. Right? Sure? Okay. Now, what we do is, to make life simple, we will restrict ourselves. So what do we want to find? We want to find the bids. What are the Nash equilibrium bids? What are the actions which will ensure Nash equilibrium? What are the actions here? The bids. Right? So we will look for bids. Bids are functions of the valuations. Right? Bids are functions of the valuations. We will look for specific type of functions. That is, we will look for BI, okay, is equal to and okay, right? These are called linear strategies. And we look for Nash equilibria in linear strategies. We look for Nash equilibria in linear strategies. Okay? Look for Nash equilibria in linear strategies. Is this clear? That will make the mathematics simpler, but that does not mean that we are not saying that there are no, but the cost will be, we will restrict ourselves only to Nash equilibrium linear strategies. That does not mean that we confine ourselves to linear strategies. All that we are saying is that we are looking for equilibria which involve only linear strategies. Right? The equilibria that will be involved will only involve linear strategies. Okay, right. So we are sure, is this clear? Okay. So now, so fine. Now what we really have is now remember, this probability will essentially be zero. This probability will essentially be zero. Why is that probability equal to zero? Yeah? Why would that probability be essentially zero? Because what is the distribution of Vj? Vj is uniformly distributed between 0 and 1. Right? Okay, now you know that for a continuous distributed random variable, the probability that the random variable takes a specific value is 0. A uniformly distributed a continuous random variable takes values over intervals, not at specific points. It would be silly to ask for the probability of if you take a variable which takes all values between 0 and 1, then the probability with which it takes one specific value is 0, because there are infinitely many such points. Right? Okay, therefore we can get rid of this probability. This will be 0. So our problem gets simplified now to looking at this. Okay? Right? So our problem becomes simpler. We just have to look at Vi minus Bi into probability Bi greater than Bj of Vj. Okay? Right. So now, but what is Bj of Vj? So what we are saying? We are looking for the probability that Bi right? which is nothing but which is nothing but the probability that Vj is less than Bi minus Aj upon Cj. Everybody gets that? Just a
Yeah.
transformation.
So,
Yeah.
you said that the probability there is equal to 0 because it's a specific point.
Yeah.
It's not a continuous rule. Isn't this probability also specific?
No, it is Bi greater than Bj.
So
So we
it's
look
like
at
upper limit is
yeah,
not
it's an
equal.
interval, right? Okay, right. So Bi greater than Aj upon Cj Vj. So this clear? So essentially looking at Vj less than Bi minus Aj upon Cj. Now the point is, if you have a random variable distributed between 0 and 1, what are we really looking for? Okay. Now look at the distribution between, say, distribution of, so Bj is distributed between 0 and 1. So Bj will be distributed between Aj and Cj. Because Bj is distributed between 0 and 1, Bj, right, will be distributed, this is Bj, Bj will be distributed between Aj and Cj. Right. What am I asking for the point? I am saying, so if I take this point somewhere as Bi, suppose this is the point Bi minus Aj upon Cj, right? Suppose this is Bi minus Aj upon Cj. I am looking for a probability that Vj takes a value, okay, in this interval. Okay, I am looking for the probability that Vj takes the value in this interval, right? Vj takes the value in this interval, right? Now for the uniform distribution, we have an important property. It says that this probability is nothing but Bi minus Aj upon Cj. Probability that a random variable, uniformly distributed random variable takes a value less than x is x. Right? The probability that uniformly distributed random variable over an interval takes a value less than x is nothing but x, because you're measuring all the area from 0 to that point. Right? So you're measuring the area under the curve up to that point. So it's nothing but x. Right? So therefore, this problem then becomes, I'm trying to maximize, right? So I'm simply trying to, so my problem becomes much more simpler now. My problem simply becomes, instead of this, I can write this. Okay? This becomes so to maximize this. Now life is simpler. So how do I do this now? I difference with respect to Bi. Right? Okay. So this becomes, so maximize over Bi
Minus Bx.
minus Bi minus Bi square plus, yeah? Sure? So how do you solve this? Yes, friends? You difference with respect to Bi and set that derivative equal to 0, right? Okay. So by setting derivative equal to 0, what do you get? You get Bi upon Cj, right? Minus 2Bi upon Cj, right? Plus Aj. This is the first order condition. This is the first order condition. Right? Now given this first order condition, I can take out Cj from all sides. Multiply throughout by Cj, I get this. And what do I then get? I get Bi is equal to Vj plus Aj upon 2, right? Okay, Vj plus Aj upon 2. Okay, if Vi is greater than equal to Aj, and simply Aj if Vi is less than Aj. That's what you get is, it's quite straightforward from there, no?
Yes.
Okay, so Vi, so 2Vi, so what you get is Vi, the solution is Vi plus Aj upon 2 if Vi is greater than Aj, but if Vi is less than Aj,
If Vi is greater than equal to it.
greater than or equal to Aj, right? But if Vi is less than Aj, then obviously you just get Aj. Right? Vi is less than Aj, because what's going to happen is, yeah, if Vi is less than Aj, then you just get Aj. Can you see the point why? That's something I leave you to think about. If Vi is less than Aj, then you just bid Aj. Because what is Vi? Vi is your valuation.
Yeah.
Okay?
Yeah.
Right? What is Aj? Aj is your competitor's least valuation. Right? So if your valuation, if your valuation is less than the lowest point of the competitor,
Then obviously
the best you can do is to bid what you bid that lowest value. Right? And therefore Aj if Vi is less than Aj. Sure? Now having obtained this, we run into some very interesting ideas. So basically, my best response function becomes yeah. So this is the best response function. Okay. Now let's think of Aj carefully. Okay. Now remember, suppose Aj lies between 0. So we must think carefully of what Aj is. So how much you bid really depends upon what Aj is. So let's think of all the values that Aj can take. Aj can be either less than 0, or between 0 and 1, or above 1. Those are only three possible values that Aj can have. Aj can be either negative, less than 0, or it can lie between 0 and 1, or it can be greater than 1. So first let's rule out why Aj will be between 0 and 1. Okay. If Aj is 0 and 1, right? If Aj is 0 and 1, then sum of the Vi's will be less than Aj. See, because Vi is distributed between 0 and 1. If Vi is distributed between 0 and 1. If Aj is also distributed between 0 and 1, then some of the Vi's will lie between 0 and 1 and some will be less than Aj. Some of the Vi's can be greater than Aj. Which means that your best response function will be Aj, right? So it will be your best response function will be Aj for some Vi's, and then Vi plus Aj upon 2 for some Vi's. So it will have to be non-linear. which we are ruling out. We are ruling out nonlinear response functions in equilibrium. Right? So therefore this means that this cannot be the case. Right? So AJ cannot be between 0 and 1. Okay? Can AJ be greater than or equal to 1? Can AJ be greater or equal to 1? Remember, okay, what is BJVJ? BJVJ is AJ plus CJ, right? Now, CJ must always necessarily be greater or equal to 0. CJ cannot be negative. Why cannot CJ be negative? Why cannot CJ be negative? It means that with higher valuation you are reading less. Right? So CJ has to be greater or equal. Now if AJ is greater than 1, right? If AJ is greater than 1, so think of AJ as 1.5. Okay? Let CJ be 0.5 and say DJ be 0.75. So what is BJVJ? BJ will be some number much bigger than 1. But the maximum valuation that the other player can have is 1. So it will be silly to bid so much more. Right? And therefore AJ can never be greater than 1. Right? So what does it mean? If AJ cannot be between 0 and 1, if AJ cannot be greater than 1, AJ has to be less than or equal to 0. Because AJ cannot be greater than 0.
Can be greater than 1.
Yeah, it can be greater than 1. It can also be greater than 0. We have ruled out this, right? AJ lying between 0 and 1 is also ruled out. AJ lying between 0 and 1 is ruled out. AJ lying above 1 is also ruled out. So what are the only possible values for AJ? Less than or equal to 0. Right? Less than or equal to 0. Sure?
Yes.
Okay. So if AJ is less than or equal to 0, what are you left with? Right? So you should be, so what is the best response function? Right? This was the best response function, right?
Yeah.
Now, VI can never be less than or equal to AJ now, because AJ is less than or equal to 0 and VI is between 0 and 1. So this must be the best response function. VI plus AJ upon 2. Right? VI plus AJ upon 2. Okay, so we have the equilibrium. Okay, so what we must have is we must have is we have VI plus AJ upon 2, right? You have VI plus AJ upon 2, right? Okay, VI plus AJ upon 2, right? So this is VI, right? So what do you have here? 1 upon 2 VI plus 1 upon 2 AJ. 1 upon 2 AJ, right? 1 upon 2 VI plus 1 upon 2 AJ is the best response function for the ith player. What is the best response function for the jth player? Bj plus AI upon 2. Okay? Right? Which is? Right? Is 1 upon 2 Vj. Correct? Okay? Sure? So, what is this really? Okay, this has to be the same as this is the same as AI plus C is equal to Ci plus Vi, because we are looking for equations of this kind, which means that CI must be equal to half. And AI must be equal to half AJ. AI must be equal to half AJ. Right? AI must be equal to half AJ. Right? Or similarly, okay, AI must be equal to half AJ, and similarly AJ must be equal to half AI.
Yes.
Right? Which means that AI and AJ both have to be 0. Right? See, because what do we have? We have from this half AJ is equal to AI and half AI is equal to AJ. What AI and AJ can satisfy this? 0. So AI and AJ is 0. So we have a wonderful result. What does it say? I tell you why it's so wonderful. What do we have is, so VI is half VI. Okay? And VJ is half VJ. Right?